fully saturated soil. Right? In between, in this case, we call it partially saturated or unsaturated soil. So this makes the soil nutrients very complicated because now you have capillarity and the suction pressure because of the water meniscus with the air, etc. But fully saturated soil and dry soil and partially saturated or unsaturated soil, that is the common status that you meet in the field. So then, let's generalize this picture because it's the most general case. Right? You can draw the phase diagram using this one. So phase diagram. So if you expand the picture to the bottom picture, you can draw a rectangle composed of three phases: air, water, and say the solid. And this is a phase diagram. We're going to use this phase diagram a lot when we calculate the density of the soil. Let's think about the density first. With the dry soil. Thank you. So I have three different soils here with a different water content or water weight ratio, but the volume is the same. I intentionally mixed it to be pretty much the same volume, not, but let's assume it has the same volume. Okay? So in this case, because it's a submerged soil, you only consider the soil of this part, ignore the water part. Okay? So when you compare the density of these three different soils, dry, unsaturated, and fully saturated, which one will have the highest risk density?
Fully saturated.
Fully saturated. Why?
Because there's water particles in void, so it has higher mass the same volume.
Within the same volume. So simply because air is lighter than water. Right? So that means that depending on the fraction, volumetric fraction between these two phases, it makes a different density. Right? So we have to define. First, when we characterize the soil by the density, we have to define what's the volumetric ratio between water and solid and water and air. So that's what we want to define first. Volume ratio. So there are three volume ratio and one mass ratio. So today, let's consider that we are learning the geotech language. These are the definitions that we need to memorize, and people use this terminology all the time. Let's define each volume first. I prefer to use the left side of the volume. And right side in mass. Here, this is the VA, the air volume, and water volume, and solid volume. And when you combine the air volume and water volume, that's the volume of void, or volume of pore volume. Right? So we call it V sub V. And total is I'm gonna write it down again. dt. So that's a total volume. Here, total volume is solid volume plus void volume, and solid volume plus water volume plus air volume. And void volume is simply the water volume plus air volume. First ratio that we're going to define is the void ratio. This void ratio, we use the small e to denote this void ratio, and the definition is the void volume over solid volume. So this void ratio is expressed as decimal, and at least you need to use 2 decimal. So 0.62 or 0.623 or 3 decimal is needed. And it varies between 0 to infinite. So theoretically you can go up to infinite. But typically when you meet the soil in the field, it generally shows a void ratio of 0.3 to 1.5 of A. 0.4 to 1.0 for sets. That's one definition. And porosity. Second porosity. And here we use small n and the void volume over total volume times E. So this is expressed as percent. So for example, 10.3%. What will be the range of the porosity? It varies from 0 to 100%. Or if you use the decimal, 0 to 1. If the porosity, 100% porosity means there's no solid. Right? 0% porosity means there's no pores. It means solid like a very like a plastic material. It doesn't have any void space inside. Then we can actually, if we know the void ratio, we can calculate the porosity, or if we know the porosity, we can calculate the void ratio, vice versa. How? So last one is degree of saturation. Degree of saturation, we use the capital S, and the W over void volume times 100. So we use the percent numbers. No? Ratio, actually it's a ratio of the water volume to void volume. So void ratio tells you the ratio between the void over the solid volume, and porosity also tells you the void volume over total volume. So these two doesn't care whether there's water or not, right? So it's only about the solid versus empty space. Right? This parameter tells you the information about the water volume pressure. Okay, so this is very important parameter. Property as the important parameter. Now we're gonna go over and move on to mass ratio. At least this case I done again. Red one in this case. M sub A will be the air mass, water mass, and solid mass. Total mass. But comparing to the solid or water, density of air is very small, right? It is insignificant. So we assume this is always 0. So basically, the total mass is the sum summation of the water mass plus solid mass. In the mass ratio, we only define one ratio, which is for the water content. And the water content is we use the small W, small letter. And this is defined as the water mass over solid mass and so on. So, the question is, how can you define or determine the water content? So this is very moist and wet soil, and water, right? We want to know what's the ratio between water mass over solid mass. How can we define that? How can we perform a test? Think about the testing procedure to get the water content. To describe in more detail, you need to have a container with known mass. So we measure the mass of the container, that's the MCOM, MCOM, and you took this soil, so maybe you can scoop several scoops and then put it inside this container. This is wet soil. And you measure the mass, that's going to be M1, is the M container plus, and mass soil. And place it in the oven. Oven dry for 24 hours at 105 degrees C. And then the M2 will be the summation of the container mass plus the dry soil mass. So here I don't have to write it down, but the water mass. How much is the water mass? What's the equation to get the water mass?
M1 minus M2.
M1 minus M2. And the solid mass will be M2 minus the container mass, right? Then you can get the water content according to that definition. Okay? And 1 minus n2 over n2 minus n from times Then we want to talk about the density. I brought the phase diagram again. We have air volume, water volume, solid volume, and void volume, and water volume, right? And we have air mass, water mass, and solid mass. The air mass is 0, so that this is total mass. Right? First, we want to find the total density. Actually, 1, 2, 3, 4. There's 4 types of density in soil. The total density is sometimes we call it wet density or moist density. And this is rho T, and the total mass over total volume. So this is solid mass plus water mass over total volume. Typically, the value ranges from 1,000 to 2,400 kilogram per centimeter. The total density reflects the in-situ condition, the field condition. If you take a sample from the lab, you may have a water or air together, right? And you measure the total mass, and if you know the volume of the excavated area, then you can calculate the total density. That's how we determine the total density of the soil. And the second is density of the water. Or water density. W is NW over VW. For ordinary temperature, what's the density of the water? Sure. Some people said rho W is just 1,000 unit kilogram. It's a cube, huh? Okay, cubic meter. 1,000 kilogram per cubic meter. Or 1 gram per cubic centimeter, or 1 gram per millimeter. Or 1 megagram per millimeter. So mega is 10 to the 6, so I think that's the value. Density of granite. So density of solid is defined as like mass, solid mass over volume, solid volume, and it's actually the density of this mineral. So, like if it's quartz sand, then the density of the quartz will be the solid density. If it's gold, maybe then it could be higher than the normal soil, but still it's a denser soil. So, depending on the mineralogy of the soil, the soil density can differ. Have you heard of kaolinite? Have you heard of silica sand? Have you heard of calcite? So there are all kinds of minerals that makes our earth, and depending on the mineral type, the soil density can differ, maybe ranges, but in general, in the very near surface that we are encountering, that we are dealing, it ranges from 2500 to 2800 kilometers per centimeter. And also here we can define a specific gravity. Solid. Here we use the notation G sub S because it's convenient to use the luminous parameter. Gs is defined as solid density over water density. So basically we normalize the solid density with the water density to see how heavy the solid particle is. So if the solid density, for example, if the solid density is between 700 kilogram per cubic centimeter, then what will be the GS? GS will be 2.7. So most soil has the specific gravity of 2.65 to 2.75. So in average we use typically 2.7. So dry density. Now we will talk about the dry density of the soil. Dry density is defined as the solid mass over total volume. So, when you measure the total density of this soil, this is perfectly dry soil. You can measure the mass, and you know the volume. It says the volume is about maybe 170 milliliter. So you know the volume, so you can calculate the total density. Right? So if I add water to here, say now it's raining, the rainy season, it's the summer. So I'm adding water. Still the volume stays constant, volume is same. What about the total density? The total density increased? Total density has increased. What about the dry density? Dry density is the same, because it's now affected by the water presence. So this dry density is used to describe how well the soil is compacted. If you compact the soil very well, it could be very dense soil, and regardless of the water presence, it could be fully wet or it could be fully dry. So the dry density will be. So the dry density is defined as this, and this is very important parameter because it's now affected by the water. It's good for judging of degree of compassion. So saturated density is kind of a virtual or imaginary density, which is the density when all voids are filled with water without changing the volume. So the total volume does not change. So in this case, say that you have a soil with a void, and imagine that this air void is all replaced by the water. Now you have water replacing the air. Then you draw the phase diagram. Water for the air. And to get the saturated density, you have to fill this air void with water. So now this is the place with water. Okay. So all the voids are filled with water. Here the MW prime, the second term, is the mass that's filling the air void. Okay? So this MW prime can be calculated by multiplying the volume of air times water density. In other words, the voids are all filled with water, so the void volume times water plus soil volume will be the total mass. The last one, submerged density. This is the last density that we will learn today. Submerged density sometimes is called buoyancy. Low stop or low prime, and this is defined as low saturated minus water. So the saturated density minus water density gives you the thermal density. Why are we subtracting this water density? So actually, submerged density can be applied to this case when the soil is fully submerged, okay? Like an underwater soil or in the riverbed or oceanic soil. In that case, the soil type will feel the buoyancy force, like Archimedes principle. So that's why we are subtracting this water density. So soil is